Right, and it is my pleasure to introduce our first speaker, Sebastian Els, who is going to talk about the science system on board the Rashid Rover of the Emirates Lunar Mission. All yours, Sebastian.
All right, thank you so much. I'm sharing my screen. I hope it's visible. Okay, and I do this in full screen mode, I guess. Okay, so yeah, hi everyone. My name is Sebastian Els. I'm a project scientist together with Dr. Sarah Al-Meini of the Emirates Lunar Mission, and Dr. Hamad Al-Marzougi is the project manager. And I'm happy to be here on behalf of the entire development team at the Mohammed bin Rashid Space Center in Dubai and our science partners who are participating in this endeavor. So some of you might have heard already of the Emirates Lunar Mission and the Rashid Rover. The Rashid Rover is quite a small rover. It's 10 kilograms. We are aiming for an operational time on the lunar surface of, well, up to 1 lunar day. Realistically, this means between 8 to 10 Earth days. And we hope we get a wake up on the 2nd lunar day. Transportation is done by means of a commercial provider, namely iSpace, and the rover engineering model at the moment is undergoing testing, and we are hoping for a launch in late 2022. Now, let me start before we jump into the science system to give you a bit of the background when the mission started, the development phase started. What were our objectives? And ELM is primarily a technology demonstration mission and we want to demonstrate and enable the national capabilities to develop and operate a rover on the moon. And science is objective number 2. So as in so many missions, science takes kind of like the second priority in this list, but I think we have come up with quite a neat package on board this quite small rover. The high-level science requirements and objectives for the Emirates Lunar Mission, I'm not going to talk you through all of those, but the last 2 bullets I think are the crucial ones here. The investigations, meaning the abilities of the instruments which we are deploying or which we are having on board, shall not target only a singular location or area on the moon. So because in the beginning we did not know where we exactly would land, we decided that, okay, the instruments have to do what they are supposed to do wherever we are on the moon. And the last bullet is, I think, quite interesting for everyone. So the data will be made available to the entire scientific community by means of an archive, so everyone will have the ability to get to these data at some point in the future. No? Okay. How does this boil down to technical requirements? We also said that the science goals of the instruments shall be independent from each other. So it's not like that we have 2 instruments and both instruments have to work in order to fulfill the science goal. That would be not particularly robust if one thinks about it. But we of course want to have synergies between the different instruments, meaning that we can correlate the data between them. We don't want to have any moving parts, low power consumption, and the total mass was less than half a kg. And this is basically what we came up with. So marked here are the instruments which are directly related to science. So they also marked the 2 cameras. We have a set of long mirror probes. We have a microscope, an optical microscope, a small thermal imager, and a little material experiment, which we call MAD, which are material samples on the wheels. And I'm going to talk here now quickly through these various instruments. Our rover has 2 main cameras, camera 1 and camera 2. The camera number 1 is on the mast at a height above the ground of approximately 70 centimeters. It's gimbaled. It's quite a wide field of view, so 85 by 85 degrees. And it has been provided to us by a collaborative agreement between the French Space Agency and MBRSC. Also Cam 2 falls under this agreement, and both cameras are essentially identical. And the intention here is that camera 2 can be a backup in case that a Mars deployment fails, because obviously for transportation to the moon, the mast is folded down. So in case it does not deploy, then we have camera 2 as a backup. But obviously camera 2 can also be used for doing some good science by, for example, observing the drive tracks on the regolith. Now the microscopic camera which we have, the objectives are primarily to determine the particle size distribution of the lunar regolith, and maybe to also perform some basic petrographic studies. I have down here the graph, the cumulative particle size distribution, from which we have inferred our resolution requirement, and we want to resolve particles down to about 30 to 40 microns, approximately. Why doesn't this jump? Okay, so here is the camera design, the microscopic camera design. The camera is mounted at the front of the rover, pointing downwards, slightly forward. And below, in the picture below, you see actually the engineering model. So that's how the beast looks like. It's a quite compact package, yes, we are undergoing testing. We have been obtaining test data already with it.
2 minutes.
Oh, okay. So this is the first light image. The Longmire probe instrument. So here you see the electron density above the lunar soil, and the rover body actually falls straight into it. So we have deployed 4 Longmire probes at different heights, and we hope to be able to probe and measure the vertical density distribution. So these are actually cylindrical Longmire probes of 80 millimeter length, which you can see here. The thermal imager is just a COTS device, commercial off the shelf. So we're just taking this with us, and we want to see, does it work? Will it work? It's more like a, yeah. If it works, it would be great, and we can do some thermal studies as well. And MAD is what we call the material adhesion or abrasion determination experiment. So basically, it's very simple. On the wheels, we will deploy different materials, and we will observe how these materials interact with the regolith by means of the camera 1. We also have a little experiment on board, which is called passive regolith sampler, but I'm not going to talk about this here. This would go too far. So with this, I just want to say thank you to all our partners. We have actually a number of researchers in the team, and they are developing the data collection and analysis methodologies, and they're going to perform the initial scientific exploitation. And I really would like to acknowledge their support and guidance in this endeavor. Yeah, and finally, ELM is conducted at the Mohammed bin Rashid Space Center in Dubai. Thank you so much. And with this, are there any questions?
Thanks, Sebastian. Yeah, I think we have time, 1.5 minutes. Nelly, do you want to handle those?
Thank you very much, Sebastian. If there is any question from now 40 participants, like you can see, I'm keeping count. Would you like to put it in the chat so that we could all share it? And while you are all typing, maybe I could start with a question, Sebastian. Where will the rover land on the moon?
Yeah, we are going with iSpace, so we are going Lacus Omniorum.
Okay, good, thank you.
I'll actually get in a quick question too. I know you're saying holding off on the adhesive materials, but are you doing that within, do you have an initial set of materials for that adhesion test kind of already triaged?
Yes, we have a list of different materials, and yeah, but if there are suggestions for more, I mean, this is the only thing which is really easy to tug on, right? If you have a material and you want to tug it on the wheel, that's relatively easy to do. So yes, if there are suggestions, please.
Thank you for the response. There is another question in the chat from Daniel. Is there a nominal distance that the rover will travel over the 8 to 10 Earth Day mission?
That's an excellent question, and I think everyone who's been doing a rover mission has been going through the same thought experiment. Yes, we have a number, but I'm not going to say here a hard-coded number. So we want to get as far as we can, but of course, if there's anything interesting along the way, then we might stop there and look at this under all sorts of different angles. And this will take a lot of time, but you are not going to make a lot of drive distance. So I'm a little bit hesitant to say here a nominal distance, to give you an exact figure.
Fair enough. I hope it answers your question, Daniel. Is there any other question before we move on to the next presentation? Thank you so much, Sebastian. It was really, really interesting.